Okay.
Everyone, hey, I'm Igor,
This is Yuva.
and we're going to talk about the overview of Yahoo Data Center Fabric version 3, which is a basically how to build CLO networks. So we're going to cover what's actually a CLO, different CLO topologies, details, operational, what we've actually seen in real world, scaling, automation, etc. So first of all, what's a CLO? Everybody thinks that it's an acronym. It actually isn't. A CLO topology is named after Charles Clow, who published a paper in 1953. You guys can read the paper name over there. I don't need to repeat it. But essentially, in 1953, a mathematician called Charles Clow, he came up with a concept of a multi-stage network that is based on an ingress, middle, and egress stage that forms a non-blocking topology and mathematical representation of it. One big thing that he came up with is that this topology can be recursive, so it can grow almost infinite scale. And this is what everybody actually calls a leaf spine design. It's actually a folded CLO, which is a CLO that is folded on itself. A very simple way to think about a CLO is something called a Binet network, named after Vaclav Binet, who is a Czech mathematician that came up with an easier way to think about the paper that Charles Clow wrote. As you can see, this is a Binet network that is effectively built out of radix 4 switches in order to create a radix 16 infrastructure. And what you're looking at is an ingress, a middle, and an egress stage. And the middle stage is recursive, which itself was made out of an ingress, middle, and egress stage. This is a stereotypical CLO topology on how to build something that's bigger than the smallest radix element of the network. Now, not surprisingly, people have been using CLO for topologies for many, many years, starting with Bell switches, like actual plain old telephone switches. And most routers and switches these days are actually small CLO topologies in themselves. About 20 years ago, people were still making switches using crossbar fabrics that fully interconnect every line card to each other. But in the last 15 years or so, most of the switches are actually made out of individual line cards and fabric cards. Line cards interconnect with fabric cards, actually forming a CLO topology inside of an actual big chassis. Also, most modern line cards these days that are using multi-chip architecture are built in a CLO topology themselves of how to interconnect from the front-facing ports, potentially to the switching ASICs, and then from there to the fabric ASICs. So one way to think about a CLO topology is something we call a virtual chassis. This is like what a chassis kind of looks like. Leaf is a line card. Spine is a fabric card. And if you think about a CLO topology like this, it's essentially one massive switch. And the way that you kind of think about this virtual chassis topology design is that all interconnection that goes in and out of this topology goes through a leaf. Essentially, just like in a large chassis, unless you do a multi-chassis system, you don't interconnect through the fabric. Everything goes out the front side. Like any CLO topology, the scaling characteristics here are the port count on the spine dictates how many leaves you can connect, and the number of spines dictates how much of a subscription you're going to have. Another possible design is a virtual line card. There's a lot of line cards that are built this way, which is ports connected to a backend fabric. Mathematically, this is the same, actually, three-stage CLO, but this is only 2/3 of a three-stage CLO that is represented here. And then you have multiple of these building elements that are either 32 TORs or maybe 48 TORs, like in Facebook's and LinkedIn's blog posts that they've posted, that you connect many of them through a common fabric. In fact, you can interconnect them on multiple different planes, creating multidimensional networks. And in fact, these aren't mutually exclusive. There's a lot of topology because CLO, you can do a lot of recursion in order to scale it out. Every one of these fabs could actually be a virtual chassis. Every component of a virtual chassis could be a virtual line card. You could use virtual chassis off virtual line cards, and vice versa. Many, many different ways you can put together these topologies. And typically, these connect to a common fabric. So as we were putting this presentation together, I found this slide deck that I used in 2008 at NANOC 40, where we were talking about the need for 100 gig. And this is what we were building back in 2006. And I look back on this and kind of look at it, wow, we were talking that this is way too many paths, way too many cables in 2006. Boy, did we not realize what we're going to build today. So without further ado, you going to talk a little bit about what we're building 2012.
Yeah, so from 2008, you guys have seen the pictures from before. Now, fast forwarding to 2012, that was the year that we actually deployed the first CLOS design in our data centers. So now, since then, we have different sizes of clusters in production, and they could scale to up to 20K 1,000 node. And theoretically, with today's devices, that they can even be scaled even larger. This is basically the ability to scale, and the blast domain is basically the trade-offs right now.
Yeah, so that's actually a very big thing when we were doing this design. Blast domain is kind of two components. One is how much will you lose at any given point if you lose this entire topology for whatever reason. Another one is we wanted to kind of build building blocks that we could evolve as technology evolves. So as new chipsets come out, higher radix, lower radix, faster, whatnot, we didn't want to have to replace the entire infrastructure. We only wanted to replace a building block of an infrastructure. And that to us was a really big driving point.
Right. And we also have, we built many clusters with different variants of sizes, and then we can actually interconnect them with a fabric layer that's on top. We are going to see the details in the next few slides. Also, we have different speed. So the ability to deploy different sizes at a different time give us the abilities to deploy different technologies at different time. So we have the old one that are running 10 gig to the servers. And now we could have like 25 gig and 100 gig in the core into different places in the data centers. For the overview, we have these clusters are all running on layer 3, dual stacked, all BGP based, and it's fully automated. We will see in the next few slides about the details. So the high-level topology. For the high-level topology, we can see that on the top we have a DC WAN aggregation layer, and then underneath there we could have one or more clusters that are interconnected through a fab layer. So the egress of each of the clusters are through a type of devices we call egress routers or EGRs. We are going to see that detail, but in any case that each clusters could have one or more, or better case is 4 or more EGRs in each of the clusters, then they are interconnected with the fab devices. So zooming down to each of the clusters, we are seeing like either they have a number of VCs, or the typical number of VCs in our environment are 4. And the TORs, each of the TORs are interconnected with each of these VCs. The number of the TORs that are available that in each of the clusters varies, and then the typical size is 512.
So if you think about the origin for this design was kind of, we used to build these 4-post networks made out of 4 really biggest switches that you could buy on the market. The design is kind of similar. We just changed instead of one big massive piece of iron, we replace it with, well,
VC. Right. Right. So, and we can build our VCs as demand, basically, right? So if we actually need a more oversubscription or less oversubscription, we can build more VC to accommodate for that. So this is just a typical setup that suit our application or traffic patterns better, but it's very easy to adapt to other traffic patterns or profiles. And under each VCs, those are the things that you might have seen past, but in more detail, Igor is going to talk about.
So we've talked a little bit before about virtual chassis a few minutes ago. There are 2 big reasons for why we chose a virtual chassis type of design. The biggest one is if you look at the cost of a large-scale data center network, back when we had 40 gig, roughly 40% of the cost of the entire network was interconnect. In now 100 gig world, that's exceeding 60+% compared to the cost of the actual switches and chips. So obviously the biggest bang for the buck is going to be actually to minimize the cost of that interconnect. The way that you can minimize the cost of an interconnect is by bringing things really, really close together. So instead of using even SR optics, you can use DAC that's 3 meter or 5 meter. And a virtual chassis design lends itself really nice to this cable minimization. Another thing that we did is a virtual line card design works really well when you want to distribute kind of in pods, so to say, across the data center floor. We were migrating from a previous design to a new design, and when you do that, we had positions available all over the data center across, I don't know, 2-3 kilometers of data center floor, and it made sense for us to centralize our VCs in order to be able to plug things in from anywhere in the data center. Now, in order to minimize that cost, we had to obviously optimize for distance. And the way that we did it is that since the spines are what's in the middle and the leafs connect to the spines, we basically placed the spines in the middle, and then we had a leaf left, leaf right, with the ports that are closest to each other are kind of what interconnects, and the further side out is what goes out to the data center floor, the top of racks. Now, when we were putting this together in 2011, we obviously decided we needed a mock-up. We needed to see what this is actually going to look like, to see what we're going to have to optimize. This is a mock-up that was actually done by 2 of our best data center ops people, and the mock-up served 2 purposes. One is we needed to see what a miswire rate is going to be in a typical data center. So our 2 most careful guys, 2,000 ports, how many are going to be messed up? The answer was roughly 5%. So clearly, we needed something to make it harder to make mistakes, to make it easier to do things correctly. Also, this spoke quite loudly of the need to automation be written in order to verify the wiring. Another thing that we were joking that this is a shit ton of cable. We weighed it, 1,014 kilograms. This is literally a metric ton of cable. Now,
there were 2,000 cables here.
It's a lot of cable. Now, needless to say, we solved this. What you're actually looking at is what's in production. This is 2 separate VCs. One is from cluster A, one is from cluster B, one on top of each other, essentially. As you can see, we've spent quite a bit of time designing custom length cable bundles to make miswiring incredibly hard, because the cables are like actually designed with less than a 2.5-inch tolerance. So when we pull something out, they almost stay right in place, and it's really hard to miswire. Also, we had to custom design the racks and cable management for both handling 2 tons of cable on each side, and also making sure that this much cable, when it lays on each other, doesn't actually crush itself, because has actually could have happened and has happened when we didn't use these things. Now, for the routing topology of how it is, over to you.
Yeah. So let's switch more to the details regarding to how we actually make the routing arrangement and the protocols work. So from this perspective, this is one of the clusters. We have VCs, and all of them are running on the same AS number. We are going to see the details inside the VC soon about their routing arrangement. And each of the tours will actually run a different AS number from each other and from the VCs as well. So each of the tours actually runs each BGP peers to a single leaf on each one of these virtual chassis. And they also have the networking statement for the loopback addresses and all the host subnet, and they are advertising to each of these VCs. Here's the zoom in of each of the VCs that I previously mentioned that only has one AS number, because we run IBGPs internally in each of these VCs. Spine, in these cases, are route reflectors for the leaves. And span leaf IGP sessions are point-to-point. So therefore, that we are using actually update source in with local interfaces. Spine also have the network statement for all the spine leaf interfaces, and we aggregate together. On the other hand, the leaf also has the network statement for the leaf Tor interconnect, so we also aggregate that part. The leaves uses NetHub self for the spine leaf IGP sessions, and all the BGP NetHub's addresses are learned from BGP, and there's no IGP within the VC. And all the virtual chassis are using the same ASN, so VC1, VC2, VC3, and VC4 are always using the same ASN.
Now, there's a couple of reasons for why we decided to do this. One is we wanted to eliminate an IGP from this design, because otherwise, if you have an IGP and IBGP, you could have oscillations and micro black holes from the two protocols converging together, not at the same time. Also, the reason for why we chose to use the same ASN is that we actually didn't want for traffic to go through another Tor and bounce around. So this way we use BGP's own AS loop prevention mechanisms to stop that propagation. And a third reason is we wanted to hide old state of what happens inside of VC from anything outside of it. There's no point to anybody knowing about it because there's a remesh component outside of it that we'll talk about in a second. But it essentially hides a lot of the complexity of all that cable mess and all the bounces that might occur if a device goes down or if somebody accidentally sticks their hand in and gets a cable loose, it will hide it from all other planes. And that was an important component to our design.
Yeah, so to that point, the interconnect between the spine and leaf, so they are copper, sometimes they are banded, and sometimes with the temperature changes, they could disconnect, reconnect. And the way that we actually aggregate them and only advertising the aggregates hide basically all those details and the routing terms. So, okay, so here we were talking about the egress. Because we just talk about VCs and the Tors, and how do we get stuff out from there, right? So we use these devices we call EGRs, is Egress Router. It's actually the same classes of devices as the spines and leaf. And however, the EGR topological-wise are like Tors. They connect to each of these VCs and using a distinct AS number. And they are distinct among themselves and also distinct from any other Tors within the same cluster. So these EGRs are special. Each EGRs connect to multiple leaves in a single VC. And they also aggregate the entire subnets of the clusters.
And that's a variation on a traditional CLO architecture that typically you don't actually do path hiding inside a CLO because you don't remesh quite this early. But by introducing an earlier layer of a remesh, we could actually hide all complexity of the entire cluster, not just the VC, but the whole cluster of 20,000 potential servers away from anything else, anything that happens inside the protocol stack, like any port bounces or whatnot, completely hidden from the rest of the data center.
That's very important. And because not only just one cluster we are looking at here, we are also looking at multiple clusters. So be able to hide the details of each cluster is very important to the entire data center. So here that we introduced a fab layer, as you see from before, to interconnect these EGRs with other EGRs in the other clusters. So here that we can connect multiple ones. Here we just depicted two of them. So these EGRs runs eBGP to the fab layers above. And from there, on the fab devices, we actually use remove private so that multiple clusters EGRs can use the same ASN number. So they redistribute this aggregated out from each of these clusters to like internal IGPs, in our case, OSPF, to the DC topology.
Now, remember how I talked before that the difference between a virtual chassis type of topology and a virtual line card type of topology is whether you allow connectivity from effectively the middle stage. So inside our clusters, we use a virtual chassis topology, but to connect multiple virtual clusters together and to allow for uplink, we actually use a virtual line card model, where we have multiple planes of virtual line cards, and that's what actually interconnects our clusters together.
Yeah, so this is basically a virtual line card on top of a virtual chassis.
Yeah.
Oh, on top of 2 virtual chassis.
Yeah. Now, people talk about incast and buffer pressure, and people say, incast is not a thing, buffering is not a thing in the data center. It actually is a thing, and you have to be really careful with how you design for it. Now, even when you have completely non-oversubscribed network, as the case in the spine in our virtual chassis is completely one-to-one. In fact, some of our designs even offer speed up through the fabric. We still have buffer pressure, but that buffer pressure, a Trident 2 class device or above, can more than handle it. Now, at the leaf layer is where we actually do all of our oversubscription. That's the torque to the leaf layer. And at the leaf, we see a lot of buffer pressure, but it's still within reason for what a Trident 2 can do. But you have to be really careful with what you do there. The next layer where we see buffer pressure is actually at our TORs. TORs are actually interesting because not only is that where you do oversubscription, it's also when you do a speed change. And anytime you do a speed change of 100 gig going down to 25 gig, you're effectively going to be draining at a slower rate that you're inputting. And you have to make sure that you design properly to handle the buffers over there. And this is actual graphs that we do in real time because we'll talk about it in a couple of slides.
Yeah, so we basically have to continuously collect these metrics and then to our central intelligence in order to do any of the changes that we are going to say in the next few slides. Scaling.
Scaling. So the way you scale this architecture, like I was mentioning before, if you want to change the oversubscription, you basically you change different things. Inside of a VC, we can change the number of basically edge position, as we call them, by controlling the radix of the spine and the radix of the leaf, where radix is the port count. And it follows a really simple formula of radix of spine times radix of leaf divided by 2. That is how many positions you can create. So if you're using a Trident 2 class device, both answers are 32. So 32 times 32, you get 512 positions. You can use a barefoot class of device for spine, which is 64 ports, and use a Trident 2 class of device for the leaf, 64 times 32, 1024. You can use 2 Tomahawk class devices to get up to 8,192 positions, which can scale up to 320,000 nodes. It's up to you how big you want to make a blast domain. It's up to you to figure out what portion of those edge positions you want to dedicate to uplinks out of the cluster, as opposed to downlinks, because that's where you can kind of control oversubscription. At the TOR layer, the oversubscription ratio is really easy. It's just dictated by the number of VCs you build. If you're using, again, Trident 2s, you build 12 VCs, Trident 3s, you build 12 VCs, you're at 1-to-1. You build 4 of them, you're at 1-to-3, and you can always add more VCs as long as you have enough uplink ports available on the top of racks. Now, to connect multiple clusters in the intra-cluster oversubscription ratio, you basically can control it by how many fabs, how wide, and also how many planes of fabs, because you can add additional capacity by either horizontal scaling, you add additional EGRs, or you add additional fabs, or you add additional EGRs and additional fabs. And you can add them as multiple planes. You can even decide that some planes are dedicated for intra-cluster connectivity, and other planes are dedicated for connectivity outside the clusters. So completely up to you. And also, just like everything in CLO is completely recursive, you can even make a fab into a VC and be able to scale to hundreds or thousands of different clusters in a given topology.
Yeah. So we can almost scale this in a 3D fashion, horizontal, vertical, and depth.
Exactly. And that's an important design. And what's more is you want to be able to scale it over time different ways.
Yes. Automation. Obviously, we have been talking about the scaling. And obviously, we have been seeing the pictures of thousands of links or tens of hundred thousands of devices. So this is a lot of complexity that we have to manage. So we have to turn into automation in order to manage all these links, all these scales, all these devices. So it's not only the number of devices or links, but also the changes that actually has to happen within these clusters, because this is the dynamic environment. Somebody may actually submit a request, and something has to change. And when you have really large network, these requests that comes in really dynamically. So all of these things actually has to be managed by automation. And we basically treated the network as the CI/CD principles. And the devices and topology and configuration, we model them and abstracted them by template and database. We integrate the inventory management systems, DNSs, and with the zero-touch provisioning, they are basically bootstrapped automatically. We also separate the config intent and the config state so that it basically we have built a complete control loop by the state machines. So there is actually a talk that we did in Nanoc 68. So if you guys want to see the details, it's on the web.
And to zoom in a little more on the CI/CD principles, there was just a talk on CI/CD on the network. We take it we take CI/CD in this kind of topologies very seriously. In fact, anytime we're bringing up a top of rack, that goes through 165 states in order to actually, before it passes traffic. And with automation, those 165 states take tens of seconds. But the basic principle is that for each link, we will turn it up, no IP addresses, LLDP verify. Only after that, we will actually put IP addresses, perform ping checks. Only after that, if it passes cleanly, we'll put BGP protocols up, no routes exchange, make sure that actually sessions are established. And then one plane at a time, we will turn up the route, switch route maps, whatnot, in order to make sure there's proper route propagation, that it doesn't actually take out a VC because we've just somehow added too many routes, and now a poor old, Trident Plus class device that can only handle 4,000 to 8,000 routes didn't just blow up, and that would go through that one plane at a time. Every state transition, there's a set of scripts that verify and make sure that the network is still healthy, everything is still good, it's doing as intended before we move on. If you don't do that, running a network of the scale is difficult, to put it mildly.
Right. We also can do the canaries, right? So the automation also control the canaries because if there's something that has to be propagated in the network in a large-scale fashion, the automation is able to actually just localize it and then do the canary first, and only after the verification is successful, then move to the next session of portion of the network. So those things is what we build into the automation in order to confidently release the changes into the network.
So operational experience. What we've learned from this since running this for the last, for 6 years. This is a very stable protocol stack because we've built in all sorts of aggregation. It's been incredibly stable. In fact, in 2012, the network used to converge in about 250 milliseconds end-to-end. In 2018, that dropped down to 125 milliseconds. That's pretty impressive, we think, with running so many stages of a CLO. Something else, even in 2018, there are still BGP stacks out there that will cause a micro black hole. It is sad state of affairs. What we mean by that is that an edge ribbon update comes in, BGP processes it, and then sends out an edge rib out before it actually installs it and confirms that it's installed it into the fib, which essentially means, hi, come through me, and when I get the packet, well, I have no idea what to do with it, throw it away. It is really sad that that's still the case in 2018. Also, we've had a significantly lower hardware failure rate than we expected. When we were first deploying these, we were kind of going, okay, cheapo, $5,000-ish class devices compared to a $500,000 chassis. These can't possibly be as reliable as the chassis. We actually learned it's the exact opposite. These devices are simple. These devices also each have their own redundant power, redundant fan. They actually have better cooling propagation. They cool things better so they don't overheat as much as a large chassis. So the hardware failure rate has actually been 5-fold less than what it was with large-scale chassis. We've been actually really surprised by that. Also, it's been very easy to install and continuously manage and grow them bigger and bigger. In fact, as the network scaled by, I think, a factor of 4, since we rolled this out, the team that runs this scaled down by a factor of 5. It's amazing what happens when you have really good automation. Now, the skill set of the team definitely leveled up.
Yeah, and then to add to that, actually, so for each of these hardware failures, it actually affects smaller number of devices affected. So when we change them, it's actually affecting, pretty much the failure is isolated in certain regions or certain very limited amount of servers that will see the change.
And we can also troubleshoot them much better because in a large chassis, when you have loss through the fabric, it's really, really hard to troubleshoot it as an operator. But when the fabric is another component and you have ping available to you, or even things better, you can actually deploy code that will do continuous testing and will inform you that there is a problem, go fix it, and or potentially automatically shut down the problem because I have 2,000 pathways. It's not a problem if we shut down one of them.
Right.
Also, we've experimented quite a bit with our oversubscription ratios through the years. When we first rolled these out, we did them as 2.5 to 1 from the top of rack up, and then we did 32 to 1 for out of the cluster in between clusters, because we thought that we weren't going to have, like when you have groups of 20,000 servers, and we have several 100,000 servers in a given data center, the cross communication, while statistically is very likely to occur, is that going to be a reality? So we started with 32 to 1 there. Since then, we've gone from 2.5 to 1 top of rack to 5 to 1 top of rack, and now back to 2.5 to 1 top of rack. Just that's what our traffic profiles dictate, and it's fairly easy for us to change what the oversubscription ratio there is. For the cross cluster, we've only been going in one direction. We've gone from 32 to 1 to 16 to 1 to 8 to 1 to 4 to 1, and now we are moving on to a different topology that will not be oversubscribing them at all. This has been what's been the case through the years. We essentially thought we were going to have to build them, remove that oversubscription much faster because we expected NVMe over fabrics to become a reality much sooner. It hadn't, but finally it looks like it might. So there's actually a good use case.
I'm sure that will change the buffer management too, right?
Yeah. Also, buffer management techniques. There's this concept of an alpha value for managing buffers. And it basically says in a shared buffer architecture, what is the proportion of the total buffer that I will allow to a single port bursting? What we found is that the best value in our network, at least, has been alpha 8. Basically, 8/9 of a buffer could be allocated to any given port in order to absorb the microburst. Now, we've learned that that's not always the case, and there are some applications that really don't like alpha 8, that want something different. And in our cases, it's either the application likes alpha 8 or alpha 2. And we can actually detect when that happens because when you're running alpha 8, and even though there's buffer pressure, we very, very, very rarely see buffer drops. But when we do see buffer drops, we've actually learned that if you switch from alpha 8 to alpha 2, buffer drops go away. And there's a lot more fairness. So we've actually built automation that will detect when these conditions occur. And that's why we actually monitor buffer pressure as we do and be able to switch between the cases when as needed.
Perfect.
And I guess that's kind of it. So questions, comments, heckles? And I guess in closing, this stuff is actually fairly simple. And the reason why we have given this presentation with this much detail of configs is to make sure people understand this is simple. There's been people talking about needing to invent whole new protocols to do this. You really don't. BGP is a very extensible way, and this isn't rocket science. So go ahead, use.
Hey, hi. First of all, thank you for the feedback. Really interesting. I work for a French cloud hosting company, and we have built our own IP fabric recently, and we made totally different technical choices, mostly because we have different environments, I guess. I noticed you're not talking about any underlay versus overlay differentiation. I assume you don't handle multi-services?
This is all underlay.
Okay, okay. So next question, and it's not a trick question. Why do you have dual stack for the underlay? Why not just go only for IPv6?
Because not everything has an overlay.
Okay. Interesting response. My team would be happy to hear about that. Okay. And third and final question. I think you said you like using merchant-based silicon devices. Did you write your own OS stack on top of those, or are you like leveraging something else?
We're actually kind of in between. We use, we did not write our own OS stack. What we actually do is we work with other stacks, and we drop a lot of our own agents on top of it that take control over that stack, and we find that that's a happy medium for us. For example, I think if you, the Nanox 68 presentation talks about how we drop troubleshooting daemons on top of other vendor stacks. We drop configuration controllers on top of it, management controllers on top of it, various other things, but we don't actually take over the core stack.
Right. So this actually allows us to get like multi-vendor environment, because we could use vendor A, vendor B, vendor C. They all use different OSs on top. Then how do we actually abstract that, right? So we're basically dropping our own agent. The agents deal with whatever that the southbound talk has to happen, and basically report back to our central intelligence, where that we can make the routing decisions or make the configuration generation decisions from.
Okay.
Yeah.
Thank you.
Mm-hmm.
Thank you.
Hi, this is Paul Congdon with Telec Networks. Thanks, very good discussion. One quick question, were there any specific considerations around congestion management, and do you run any workloads that either require lossless or very low loss type configurations?
Yes, so we do not run workload that require lossless. We are very much against lossless, because lossless is nothing more than let me reserve a lot of capacity that I can't then use. Mm-hmm. A huge portion of our workload is Hadoop. Shouldn't surprise you, since we're the guys that open sourced it. And that moves a lot of data, and with our topology, we don't have issues with running Hadoop in that topology. Because again, we can control oversubscription as needed, and when you tune buffering the right way, we aren't seeing issues.
But are you doing any kind of ECN threshold setting on the switches, or
Nope.
using that? You're not doing anything like that? Okay.
So we are doing a little bit of a trick. There's a couple of methodologies to cause a fast retransmit in case of loss. For example, in our topology, we know that if a packet has been in the network for longer than 50 milliseconds, it's impossible, it's lost, because the buffer simply can't hold anymore. So we actually have a IP route setting deployed onto our servers that say, now if you're within my cluster and begin fast retransmit at 50 milliseconds, if you're within my data center, begin fast retransmit in 25 milliseconds. And the data that we have is that we can basically get to 99.997% of a lossless network with those settings alone.
Cool.
Dan Megorian, Johns Hopkins APL. Good talk. How do you handle the differences in hardware generations and the increase of TCAM that you get with different chipsets? Like, as you move from Trident to Jericho Plus to Jericho 2 now, and all that. That gives you, a lot more fib possibilities, but, if you're constrained by worst case across your clusters, then you're not taking advantage of that.
Yeah, so that's a great question. This is actually one of the reasons why we do the remesh that we do at the EGR layer, is we kind of hide the complexity of the entire cluster. So to us, a cluster is one generation. And then what the next generation is, we build the next cluster, we add it into a common fabric plane. And within that cluster, we can do whatever we can do there. We can also upgrade the fabric layer and cluster A, B, but not C. And as long as cluster C is hiding everything else from upstream, and is also everything for other clusters, you're only getting the aggregate routes, you're not limited anymore. Now, as far as Jericho versus Trident, for example, that's a deep buffer system versus a shallow buffer system. I'd be very careful with mixing them.
No, we don't.
I'd be super careful with mixing them. In fact, we don't mix those.
Yeah.
But we have gone through multiple generations of hardware as we went from Trident Plus to Trident 2 and 3, et cetera. It's basically been another cluster that was deployed, and that's kind of the building block for it.
So you tune your route handling across generations, even though each one is locked into a particular, each cluster is only one generation, but then between the clusters you tune that to take advantage?
Well, yes, because effectively, so you can, obviously, a Trident Plus might have only 8,000 dual stack routes that you can pass in, but a Trident 3, you can do 200 some odd thousand. But what comes out of what does a given cluster actually need to know? It needs to know the aggregate routes from the outside world, and maybe default for how to get to the outside world. So it's a very limited number of routes that actually need to be fed into the cluster that are from outside the cluster.
Well, then you don't care.
Right, and that's actually why we did the design, is that there's very little state that needs to be exchanged, and this is what actually helps us in both scaling and converging, is that we minimize state as much as possible.
Got it, thanks.
Sure.
Hi, my name is Anand. I have a couple of questions. The first one, with the disaggregated chassis, you have multiple levels of ECMP in the network.
Yes.
So along with it, it brings a hashing problem where the second level hashing may hash to a single link, and that could cause some head of line blocking. So have you faced some problems like that? And how did you solve those problems?
Yeah, so we have seen that problem when we were testing the very initial set of these designs. The way that we address them is that at every other layer, we actually employ a different hashing technique, and that is actually codified in. And I'm not going to give away Broadcom's IP, but suffice it to say, we use different hashing techniques at different levels, and that solves the problem.
Okay.
But you absolutely must do that, otherwise you will get polarization.
Yeah.
But every vendor I'm aware of has now a knob to change which hash behavior you use and just change them as you go up.
Yeah. The second question is, have you done any kind of cost modeling to compare this kind of a disaggregated chassis over a actual chassis?
Oh, yes.
Even the number of cables and the components you are using, is it, I know you are running for a long time, but is it economically making sense to migrate?
This is 1/7 the cost.
Wow, okay.
At least for us.
Okay.
And part of the reason is that if you think about when a vendor makes a large chassis, they're going to sell maybe a couple 100,000 of them, right? And there's a lot of R&D in backplane, cooling, etc. But small chassis are sold in millions. So they're cheaper to make. There's a lot, you can distribute R&D over a lot more. The equivalent port counts are insane, like much, much cheaper. And really, if you're interconnecting all the components via copper DAC, it's not that much more expensive than electrical PCB. So the cost of goods is significantly lower, and the fact that the R&D is spread across so much more devices makes it a lot cheaper.
And latency is not playing any role with this kind of a disaggregated chassis, given number of hops has increased with the disaggregated chassis.
I mean, the reality is that even in an integrated chassis, you're still going through all of those ASIC hops anyway. So all you've done is actually said, my electrical backplane is now 3 meters long as opposed to like 1.5, and speed of light through DAC cable, kind of fast enough.
And in our environment, it's actually bounded by the amount of buffer that can hold the packet, right? So we know how many stages this packet is going to travel through, and that's the amount of time that maximum that you can see for packet delay.
Thank you.
Yeah.
No problem.
Vincent Cilindro with Dell Technologies. For your spine layer, have you guys considered spine groups instead of VCs? And if so,
Have we considered what?
spine groups?
So we absolutely have, like I said, everything could be recursed. Yes, we have. In fact, like I mentioned inside like the fabric layer, every fab could be its own VC itself, which is effectively spine groups. You can scale any dimension that you want, any which way. For us, maximum design of 8100 edge ports was sufficient at the current thing. If somebody needs more, and those aren't host edge ports, those are edge ports out to top of rack positions. Well, we might be comfortable running 40,000 nodes, so about 15 megawatts of power in a single blast domain. I sure as hell wouldn't want to go any higher than that on a single blast domain. But that's just me.
Thank you.
Sure.
Leslie Daigle, Thinking Cat Enterprises. Really enjoyed the talk, thanks. But one question following up on the, is it cheaper than Big Iron? When you did your cost comparison of PCs, you know, a gaggle of PCs versus large boxes, and the amount of, and your comment about the amount of research, were you factoring in your own time and
Yes.
the amount of research you had to do?
Yes.
Cool, thanks.
Absolutely. And in fact, the topologies, if you scale it down to a more enterprise-friendly size, like 1,000 hosts or 2,000 or 5,000 hosts, the topology gets a lot simpler. And it actually gets to a point where maybe you don't need to build a CI/CD type of automation system. You can kind of do a build once quick script and forget, which drops the cost even lower to enterprises, like lowers the barrier of entry. Cool, right on time.
All right. Thank you, everyone.
Thanks, everyone.
Yep.